Did you say
I like the
something?
chips in your background.
The chips.
She said she wants to change her background first.
Okay.
So it looks
All right. Yeah, everyone, I'm recording right now. Okay. So today we will go through quickly what we learned last week. Yeah, last week we were learning about forces. I introduced you to what force is. And forces are pushes or pulls. Yeah. So when you push something, is the object I'm pushing closer to me or away from me? So it starts from here, then I push it.
Object will
Now
go
it's here.
and it flies
further away
and
from me.
Yes. So
and flies
yes.
around
So
the world
when
and
you
hits
when you push something, it's gonna be further from you, and vice versa. As you pull them, it's going to be closer to you. Yeah. So okay. So let's have a look at the picture on page 121. Okay, I probably should.
Miss, we can't see.
Yes, I know. I shouldn't blur my background, but let me change first. There you go.
It's they are pretending to be like
Okay, so
Ari pretending.
yes, so Ari is
Uh,
pretending to be a
horse.
king in a horse cart, but instead of a horse cart, it's actually a Smarty cart. Yeah, it's not pulled by a horse, it's pulled by Smarty. Okay, so when
Oh, Smarty.
Smarty
It's a
is
robot.
the
She's
robot.
gonna trip.
Smarty's a robot.
Yeah, this is Ari, this is Tom, okay? So Smarty is pulling the cart and Tom is pushing the cart. So is the box here coming closer to Smarty or further away?
Coming.
Closer.
It's coming closer, yeah, because Smarty is pulling. Now, well, Smarty and Tom, I'm gonna draw it on the board. Yeah, so forces can come from many directions, yeah. So for example, I'm opening the whiteboard now. Can you all see?
Up, down, left, right.
Yes.
Yeah. So forces, this is like the object, right? This is the box and Ari. So if the red one is Smarty's force, he's pulling it. And the green one is
Tommy.
Tom's force, yeah. Now, if I take away these arrows, okay, and put them in the same line together, do you think Tom is helping Smarty or making Smarty's work harder?
Helping.
Helping, why?
Because they're doing the same
They're
work.
both pushing in the same direction.
Exactly.
If Tom is pulling away, it will make it harder for
Yeah,
Smarty
look, they are moving to the same direction, even though one of them is pulling and one of them is pushing, but they are moving to the same direction. Yeah, so it's important when you think about force, yeah, where do you add the force? Where is it going? Where is the direction of the force? It matters, because if the case was different, if Tom was pulling the other way, so both of them are pulling, but look at the direction here.
It's like tug of war.
Yeah, so if I put the arrows together, they're actually moving to the opposite way, right? So it's not gonna go anywhere, yeah? One wants to go this way and the other one wants to go that way, so it's like even.
Is it like the two neck turtle? He wants to go that way and that way. But
You remember the name of that game?
you will just go the opposite of direction of war.
Tug of war, yeah. So this one over here is the concept of tug of war, yeah. So you're trying to pull, and whoever gets the flag, so there should be a flag somewhere here. Whoever gets the flag to their side of the line, yeah, they will win. Okay, so this is a game of tug of war, but yeah, my point here is force have direction, and that direction is going to affect where that object is moving. Yeah, so we're gonna learn about that today. So let's go to page 123. Okay, I'm gonna ask someone to read it aloud. Okay, how about Alexa? Alexa, can you read page 123, please? 123.
I will never admit defeat. You have to try much harder than this. A force is a push or pull. A force consists of two things, the size of the force and the direction of the force. Force are measured in
Newtons.
Newton. We can use a force meter to measure the size of a force.
Yes. Okay. So, like I said before, yeah, thank you, Alexa. So, like I said before, yeah, it matters, right? So, oh, I might have erased my drawing, but oh no, I haven't. Great. Okay. So, I was talking about the direction, right? So even though Tom and Smarty is doing two different kind of force, push or a pull, but what matter is the direction. Okay, so this one here, it looks like I'm drawing the same length of arrow. Yeah, so if the arrow is long, you can, well, I'm gonna, if the force is big, I'm gonna draw a longer arrow. Okay, so what happens is, if, hang on, where's my red part? There you go. So the direction matters, and the size of the force also matters. So if like this, okay, so I'm representing the size of the force as the length of the arrow. Okay, so if you look at this one, if Tom was only giving this much of a force, do you think he's helping much? No, yeah, he is helping, but not that much. Yeah, so how can
the force is not strong, it's not that strong.
Yeah, so Smarty is a robot and Tom is a human, so robot have more strength than us, so they're gonna pull a lot harder. Yeah, so force can be bigger or smaller, right? So this is what happens if you play this game that you see on page 123. So I want you to, well, because you don't have a sparring partner, I want you to put your hands on the table, elbows on your table, okay? And try to like face your hand this way and the other one this way, okay? Like this. And then try to push your right hand towards you, but try to push your left hand also towards you. Now, I want you...
Hold on, I know what is that.
So you can play this with your brother maybe, or your mom or your dad, yeah, but there is this game, okay, I might turn it lower. There is this game where you're trying to put down your opponent's hand or arm, yeah? So what you have to do, you have to press really hard. Okay, now I want you to press only your right hand, press it. Okay, keep your elbow on the table. Nah, okay. Now push your left hand harder. Now push your right hand harder. Okay, so yeah, you can play this game with your brother and see who's got the biggest force. Yeah, if you have the bigger force, you can put down the arm of your opponent, right? So yeah, you can feel that you can change the size of your force. Yeah. All right. So the size of a force are measured in newtons, like Alexa said. So, okay. How do you know your weight? Do you know your body weight? Who can,
I think
okay,
it was
who can tell me your body weight? Can you tell me your body weight?
Around 29.
29 what?
27.
27 what?
29 kilograms.
Kilograms, yeah?
27 kilograms. My weight is
Yeah.
30. No, my weight is 135 kg.
Oh, wow. Okay, 135 kilograms. Okay, wow. That's very heavy, yeah? So,
It's excellent because I am strong.
oh yeah, okay. You're like Hulk, yeah, like this, like that. Yeah?
You can carry 120 kilograms.
Yeah, so
If 120 kilograms, then try to lift it. And we need proof to see we can lift it.
yeah, so kilograms, okay?
49.4.
Yes, okay. So kilograms are the thing to measure your weight, the unit to measure your weight. How can we measure force? Well, we measure force in newtons. So is 100 Newton big or small?
Small.
Big, small? Yeah, well, the bigger the number, that means the bigger the force, yeah? So newtons are the unit that you use to say how big is the force, okay? And the thing to measure the force is called what? Look at the
meter.
force meter, yeah? So now you already learned so many measuring tools. You know thermometers, you know anemometers. Who still remember what is anemometers? What's anemometer? Hmm? The what?
Direction.
The direction, you sure?
Wind.
Wind speed. Yeah, animal means moving, so how fast something moves, okay? So anemometer measures the wind, yeah. So windsock measures what?
Huh? A
The
windsock?
wind.
Windsock. Windsock. I thought we ever make a windsock, Kelly.
Yeah, what is it measuring?
Wind. The direction.
Wind.
The direction, that's right. Yeah, so force meter. So anything that ends with meter, usually it's to measure something, right? Force meter, anemometer, thermometers, yeah. What else? I can't remember more. Well, I'll think about it. But yeah, meter is like, if something ends with meter, usually it's a measuring tool, okay? Because this one measures force, so it's a force meter, okay? And if you look at the force meter here, look at the tool here, yeah? It's like a pen, but the inside of it, there's a spring. Do you know what a spring is?
Yeah, a spring is something that boings, boings, boings.
Yes, exactly. So in a force meter, it's a tube with some scales, like a ruler, right? And then in the inside of it, there is a spring, like this. Okay, why is it like this? Why do you think it's like this?
So it can lift up the object.
Yeah, so what's going to happen is you're gonna hang this freely, okay? And then you're going to put something down here and see how far this spring stretches. So after I put the like a block or something heavy, yeah, or well, in your book it's a scissor, right? If I can hang something here because it's heavy, right? Remember that we have gravity. Gravity is a force, right?
Yeah. Yes.
So gravity will pull this mass or object down, right? So the spring will go shorter or longer? Longer, yeah. So it's gonna go longer like this. Yeah, it's going to stretch. Okay, and then you can look at the difference between this and this. Yeah, that's how far your spring has stretched. Okay, so yeah, my item is gonna be lower. Okay, so the difference between this one and this one, well, this one is longer, obviously, right? So it's gonna be the length of the spring, number 2 minus 1 is, yeah, how many newtons? Okay, so usually the scales here that I said on the
1 newtons, Miss Brita.
yeah, 1 newton.
Subtracting.
Yes. Oh, yes, you may go to the restroom. Okay, yeah, so usually you have to look at the scale here, okay? So later we will try to do this. I have a video for you to try, okay? But for now, well, let's talk about the direction of a force, yeah? So this is, we're talking about how big a force is right now. Now, we also know that the direction is important, right? So let's go to page 124. Let's go to page 124. Clayton, do you want to read the discover more? Come on, Clayton.
Maybe.
Okay.
Where's the discover more? Plan interactive game and try.
Wait. What page are you now, Clayton? Clayton.
122.
No, 124. Next page. Here.
Discover more.
Yes.
A digital force-meter can be used to measure forces as well. Compare how a digital force-meter and a common force-meter are used. Why is it better to use the digital force-meter than a common force-meter? Discuss this with
your friends.
your friends.
Okay, thank you.
Search to find more about.
Okay, so yeah, we're going to discuss about the digital one and the normal one. Yeah, so the one I drew just now here is the non-digital, the traditional one. Yeah, so the digital one looks like that one on your screen. Okay, so not on your screen, sorry, on your book. Okay, so why do you think that digital one is better than this one? Well, I'm gonna give you a hint. It has to do with the spring. Okay, one by one.
Spring, it uses batteries.
Which one used the battery?
The digital one?
Okay, the digital one used the battery. Well, what does it have to do with the spring? Can anyone answer?
The digital one is easier because it doesn't have spring. You just put it on and then you can see how much newtons on the screen. So it's easier than the traditional one.
Okay, easier. And maybe Jaden can help. What do you think about the spring? Why is using spring not so good? Jaden? What do you think, Jaden? Jaden, are you there? Oh yeah, okay.
Yes, miss.
What do you think? Why is the digital force meter better than this kind of force meter? It has to do with the spring. So think about digital force meter versus conventional. So conventional means this one, yeah? What do you think, Jaden? What is this spring made of?
Plastic, I guess. I don't know.
Plastic? You sure?
Or metal.
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 Yeah, so springs here, the springs here are made of metal, okay? And well, how heavy can this spring handle actually?
Because the digital force meter is more accurate.
Metal.
Yeah, so if you hang scissors or wooden block here, that's okay. But can I hang some luggage, for example, or like I don't know, can I hang heavy stuff here? No, right?
Oh,
Yeah. Yes, you may drink. Okay, so spring has limited range of elasticity. Yeah, so yes, this can stretch for now, but you know, how far can it stretch, right? If it's too heavy, of course, it's gonna snap. Yeah, it's going to break basically, right? And then, okay, sure, we're gonna use light stuff only, right? We're only going to use light stuff here. But after a few years, so I'm using this year's spring for P3A right now, but in a few years time, how is my spring going to be?
it's gonna already stretch so far.
Yeah, it's gonna be worn out. Yeah, so springs can wear out too. So maybe in the first year it would be like this. It's like tight and close to each other. And then on the second year, it will be like a bit stretched. And then after, yeah, after 6 years time, maybe my spring is already like so stretched that, you know, I can't use it anymore. Yeah. So using a spring actually has a limited use. It's not so durable. Whereas if you use digital ones, you can take heavy stuff. You can also use it for many years. So spring is not durable. It can stretch. It can, what did I say before? It can wear out, sorry.
Its elasticity.
Yeah, so when it's losing its elasticity, it's not gonna come back to a packed spring like this. Yeah, so this is the downside of using this. Well, why, Miss? Why don't we want to use a stretch spring like this? Well, it's going to affect your reading, right? If your scale, sorry, if your scale is like only up to here. So I'm gonna draw this one, yeah? If your scale is only up to here, what about this one? How are you going to read this, right? It's stretched, so there is no scales that can read your force accurately, right? So that's why we don't use a stretched out spring, okay? All right, so let's do this one over here. There's a little bit of exercise on page 124. So let's have a look together. Tom and Smarty each kicked a ball from the same starting point. Yeah, everyone look at your textbook, page 124, okay? Okay, I give you some time to what do you call that? Think of the answer and then we discuss, all right? Wait, give me a moment, yeah? I have a phone call, sorry. Okay. How are we doing? Why? Why did Smarty's ball go further than Tom's?
Why did Smarty's ball go further than Tom's? Because Smarty have bigger force than Tom at kicking the ball.
Exactly. So the size of the force will affect how far that ball goes. Yeah. So, yes, Winston.
Answer. Because Marty put more force to his ball than Tom's.
Exactly. Yeah. So, okay, well, they're using the same leg. Yeah. They're using the same leg, right? So actually, this is the importance of exercising. Yeah. If you exercise your muscles, your muscle can make bigger force. So this is why athletes, they work out a lot, because they have to, well, they have to be able to kick far, they have to be able to shoot basketball far away. Yeah. And depending on the strength of their muscle, if their muscles are strong, then they can exert or make bigger force. Okay, so if you want to be an athlete, yeah, you need to work out very hard, and yeah, you will need to be strong, yeah, to be able to make bigger force. Okay, this is also why you get tired if you're not exercising much, because your muscles are not so strong. So you feel tired when you do heavy activities, because heavy activities needs bigger force. Yeah. So your muscle strength has to do with how big the force you can make. Yeah. All right. Excellent. Now I'm going to show you some slideshows before we go to the experiment. So we're going to do a virtual experiment here. You're going to watch a video, sorry. You're going to watch a video, and the video is about, what do you call that? Force meter, yeah? So let me share you the PowerPoint for now. Okay, so if I can, yeah, I'm going to summarize what we learned today, okay? Today we're learning about the size of a force, but what is a force? Can you all see my screen now?
Yes.
Okay, so I'm gonna make it full screen. Okay, so remember that a force is pushing or pulling, and it has a direction. Yeah. Now that one is a push. Okay. So like I drew before, you have arrows that shows the direction. Okay. And the bigger or the longer the arrow, that shows that you have a bigger force. Okay. Now balance force. This is the same case as the one that you see in the, was it Ari? Yeah, Ari pretending to be a prince, yeah. So when two forces acting on an object, but they are of the same strength, yeah, if Smarty and Tom was pushing with the same size of force, okay,
Will just stay still.
it's balanced, yeah. So
Balance and will stay still like this only.
yeah. Okay. So, oh, sorry, not I don't think that was a good. I don't think that was a good example. But balance force means like if you go up for 5,000 Newton, you should also go down for 5,000 Newton. Yeah. So, if I can, the one that Smarty and Tom did was not a balance force. Yeah, it's actually like helping each other. Yeah. So, balance force happens when
It's not.
they're
If
going,
push is not balanced.
yeah, they're going to the opposite direction. That's too small, is it? Can you see it?
Yes.
Same size.
So it's like when there's a box,
Mhm.
like one person pulls the box for 5,000 Newton, then the other person on pushes the box 500 Newton, then that is balance force.
Yeah. So if this happens, do you think the box is going to move or not?
Yes. No.
Well, in different directions.
Yeah, okay, so you can think of it like a tug of war, yeah? So tug of war is going to the opposite direction, but let's say that the pulling force is exactly the same strength. Do you think the rope is going to move? The flag on the rope is going to move? No, yeah, because you're pulling this way for 5,000 and you're pulling that way for 5,000. Okay, so if I could say this is almost like adding and subtracting. Is that the word? I'm not a math teacher, but okay. So this one is 5,000 going that way. Like we can say it's maybe like plus. This one is minus because
so it's actually like when it's 5,000 plus 5,000, that means the middle is 10,000.
Yeah.
So when there's 5,000 balance, and
so if they are opposite directions, you can give them different signs, yeah, plus and minus. If they are of the same direction, you can, if for example there's another force that's pulling, there's someone else helping for 1,000 Newton, well, this one is, yeah, so the total, so you have 5,000 minus 5,000 plus 1,000, it's 1,000, right?
Yeah.
So that means 1,000 and it's plus, so it's 1,000 Newton going this way. Yeah, so I will work on these exercises more later, but what you have to know is if the force are going on the opposite direction, give them two different different signs, yeah, plus and minus, and then add them together and you can see where they're going, yeah. But for balance force, because they are of the same strength, yeah, so the total, okay, I'm gonna erase the 1,000 one here. The total here is 0. When there is 0 Newton there, that means the box is not moving. Okay, all right, so yeah, so this is like just an example of the force meter. Yes, Winston.
One thing, actually, when like balance force means like there's like 5,000, 5,000 right here.
Yeah, so balance is like the opposite direction has the same strength.
There are two 5,000. That means actually like pulling will just stay still when like the middle is 10,000. So it will just stay still like here and here.
Yeah.
Just like still.
Okay, yeah, so okay, let's continue, yeah, Winston. Okay, so yeah, this is another example of balance force. Okay, so if you have a boat, yeah, floating on the water, so the reason why it doesn't sink is because a boat is heavy, right? So it's gonna go down, yeah, but the water is also going to lift the boat for the same amount of strength. Okay, so yeah,
so it's balanced and it will just stay on top of the water.
Yeah, if it's balanced, then it can float, yeah, but if it's not balanced, yeah, if the boat is too heavy, for example, the arrow is gonna be longer, right? Remember that longer arrow means bigger force. Yeah, but the lifting force, so I'm gonna
go to the restroom, please.
Yeah, okay, the lifting force is not as much, so that's why the boat might be like not really above the water. Yeah, so like,
yes, I have one question.
Yes.
So are you telling us balance was like that? Why ships don't sink? So I think you're telling us that I think people who use boats first when they make it, they have to like know what is the mass and
yes,
how many
exactly
the water. So
yes.
later they know if it's balanced, then they can use it.
Yeah, that's why people who make boats, they have to be very, very smart. Yeah. So they have to calculate, they have to know how much this boat weighs and what if the sea is like this and like that. They have to think about that. Yeah. So,
Miss,
yes.
Miss, what happens if the boat's too light? Will the boat stop flying?
Well, not flying, but if the, you know, the water in the ocean moves, right? So if the water,
Yeah.
if the boat is too light, then it's gonna be easily flipping, right? Because the
Because
upthrust.
it will just like instant wave, like
Yeah, remember the.
light, then it will like
Yeah, if the force is too, if the force from the sea is too big, yeah, it can flip this boat, right? Because this boat doesn't give that much force to the sea. Yeah, Kellyn.
Does the gravity have put it down?
The gravity, yes, the gravity always pulls everything to the center of the earth, right? So, yeah.
Unless you're out of space.
Oh, I think
Yeah.
it's because of like the atmosphere. That's what creates the gravity.
Yes. Okay. So those are two examples of balanced force. Yeah. And oh, wait, sorry. I meant to show you the next slide, which is about the force meter. Yeah. So this is the force meter. This is the digital one. Look, it doesn't use any spring, but it still have things to hang your object down here. Okay. And this one is using a spring, and look, it has some scale. Yeah. So
I have one question.
yeah, wait, please. Wait, yeah. So I'm already explaining why this is not as good as this one, because spring can wear out too. Yeah. So if this wears out, yes, Crystal. If this wears out, then it's gonna stretch down here, and you have your spring down here, and then you get confused. How am I going to read this scale? Yeah. So yeah, it's measuring the forces that your object make. Okay, and it's measured in Newton. Okay. All right. So next slide. Now, why is it called Newton? Because of this person. Yeah. So this person, his name is Isaac Newton. He is the one who first discovered about gravity, and he is the one who, yeah, he was sitting under the tree, and then suddenly an apple falls and hits him, and he was like, why is this apple falling? Yeah, so this is a true scientist right here. Yeah, he always think about why is this happening to me? Why is the apple falling to me instead of like staying up there or flying slowly? Yeah. So why does the apple fall so fast and it hits me, it hurts me? Yeah. So he was the one who first think about this, and he discovered that the apple falls because of a force called gravity. Yeah. So he is the one who think about all these forces, and that's why we honor him and use his name as the measure of force. Yeah, like kilograms is for weight, or kilometers are for distance, for length. Yeah. Yes?
So if we put Newton on there, that means that word for measuring is special, right? A special measurement word used for scales.
Yeah. Okay.
Yeah.
So now it's time for virtual experiment. Now, please open your workbook as it says on the screen. Workbook page 103 to 104. Everyone take out your workbook, page 103 to 104. Yeah?
Page 104. Court stand, a slot with holder for weights, a rubber band, a ruler.
Okay, let's have a look at what we have to do first.
Pen, lamps.
Yeah. So the experiment is called hang in there. Okay, so the aim of this experiment is to find out how the length of a rubber band changes when different forces are exerted on it. So, hypothesis, you've learned this before. What's our hypothesis?
It's called like forces like pull. It's like pulling down like very hard because of the weight. Like I think it's called like strength.
Okay.
It's a property.
Wait, Winston, what's your hypothesis for this experiment?
I think the rubber band will break because plastic is hard, but is strong, but can break for like heavy things.
Okay,
That's
okay, maybe I will reword your I think you get the idea, but I will reword your sentence. Okay, the heavier the object that you hang on the rubber band, the further away your rubber will stretch. Yeah, so the longer. Yes.
So if it like stretch too long, that's when you know that it will like break and boom like that.
Oh yeah, yes, of course, yeah. So the heavier your object, the longer the rubber band will stretch. But at some point, if the object is too heavy, the rubber band will snap.
Break.
Yes. Okay, so that's the hypothesis. We don't know yet. Okay, remember hypothesis is before we do the experiment. Now, I'm going to play the video and let's have a look. Okay.
Do we like copy it? Do we copy?
Copy what?
Experiment.
Yeah, so you can switch to page 104. Everyone go to page 104. There is a table you can complete. Yeah, by watching this experiment, right? Okay. So let's start the video. I hope you all see this already. We don't need a sound for this, so I'm not going to share the sound, yeah?
By the way, I don't think we have enough time to actually like finish this video.
That's why, no, we do. That's why just record directly. Okay, look, that's one weight. No. This is zero weight, yeah? Zero weight added. So there is nothing added on this hook. So please record the length of the rubber band. The length is, what numbers here? 73. Okay, so that's right. This is why we will fit the time. Yeah, so take notes as we watch the video. Yeah, so number of weights added, no weights added here, and the length is 73. Everyone write 73 there on the table.
What page is this again?
What page? Workbook page 104. Ayo, hurry up, Edmund. We're running out of time.
Wait, hold on. Miss Prita.
Yes.
Like 24, like A, like 1, 0, 1, 2, 3, 4. What is that even used for?
That means how much weight is added. So later you will see that the person will add some weight here. Yeah, now there is no added weight. It is 73. Okay, look here, the number is 73. Yeah. Has everyone write down 73?
Yes.
Yep.
Okay, can I continue the video?
Yes.
Yep.
Okay, that's 73. Now he's adding one weight there. And what's the length?
71.0.5.
Yeah, 71.5. Okay, let's write it down.
How do we like point?
Just comma, I guess. 71.5.
Edmund,
Edmund, are you copying, Edmund?
Miss, do we write 0.5 or 5?
Sorry?
They write 71.5.
Yeah, 71.5. Okay. Can I continue the video now?
Yes, ma'am.
Okay. Now he's adding 2 weights. Whew, the rubber band is stretching. Okay, it's a bit tricky there. It's 69.2, I guess. Yeah, 69.2. Yeah, everyone. When two weights are added, the rubber band, the scale shows 69.2.
Well, at least that's water. That's what you said.
Yes, do we need to
Yes,
submit this?
no, we will discuss, but yeah. Sorry, who was that? Oh, wait. Yes,
Michelle.
we do not submit the activity, but we submit the worksheet. So that's why let's chop, yeah. I want you to actually just take down the numbers for now, and we will discuss it next class, okay? So can I continue now?
Yes.
Yes.
Three weights added. 66.4. Wait. Let's go back. Wait, where was it? Sorry, that's too far. No, why? Stop it. Okay, there you go. 66.4, yeah? For three weights. 1, 2, 3. Done?
Yes.
Okay. Last one.
Yes.
Oh, sorry. 66.4, yeah? For three weights added.
Was it still on page 103?
104. Who was it? Michelle Kelly. Ayo, keep going. Okay, so last one, yeah?
Last weight.
It's gonna break.
It is
Not gonna break.
63.1.
That's one.
Yeah, well, it's not exactly on 63, just right above it.
Wait, are you sure that's 62?
Wait. Actually, I think it's exactly 63. Look. Yeah, so he had to wait until it stops moving. Look. Hang on. Down. Yeah, I think I would say that was 63.
Yep.
Okay. So let's double check, yeah. For zero weight added, it was what? 73.
73.
And then one weight,
71.5.
71.5. Number two, two weights added.
69.2.
And then three weights added.
66.4.
And the last one?
63.3.
63. Okay, yeah. Keep that data for now. We're going to discuss it next class. Okay, now you go to the other page of your workbook, which is on page 109. Yeah, page 109.
Miss, we don't have enough time.
We
It's 12
do.
o'clock already.
It's very quick. Okay, it should be very quick. Yes, I know. That's why it's very quick. Come on. We also started late. That's why we don't have enough time. Yo, this should be quick. Push. So you only need to write push, pull, or both. Yeah, push and pull. Do you do it yourself? Okay. Well, I'm not discussing this because we're going to submit. Yeah. So it's until page 110. Yeah. 2 pages there.
Well done.
Sorry, Kelly?
I'm done.
Blowing a candle. Done.
Well, when you blow a candle, what happens to the fire?
For flying a kite, is it the force of the kite or the girl who is
The girl's force.
push and pull?
You can write both too, right? So yeah, it might be the answer.
She like pulling the air inside and push it there, right?
Okay, everyone, listen, yeah. No need to submit that experiment. You only need to submit this worksheet, okay? So only submit page 109 to 110. Yeah? It should be very quick. It doesn't even take 5 minutes.
Very quick, but not really that easy.
I'm done.
Done? Okay, if you're done, you can close your book, clean up, and we get ready to do greetings. Winston done too. Don't forget to submit, yeah. I'm going to make the folder soon. Yeah, everyone, you have 3 more minutes, yeah? And then we do greetings, okay?
So we finish at 12:05.
Yes. Clayton, done, Clayton?
One of them is with yellow hair, and I like that girl.
Oh, yellow hair. Oh, you mean blonde hair? Yes. She's pretty, right?
She's cute.
Yeah, like Clayton also cute.
Like Miss Daisy ya, Clayton.
Oh, Miss Desi. Miss Desi also cute.
Miss Prita is rhymes. I think he said
Miss Prita is like a pizza because I'm wearing red. Okay, who is not done? Who is not done?
well, I'm confused one number.
Edmund, are you done? No?
Almost, miss.
Oh, almost. Yeah,
Almost.
good. Edward, are you done, Edward? Yes? Okay. You look handsome today, Edward. Is that because of your clothes? I think, yeah. You look, yeah, and new hair. That's nice. Everyone is brushed up today. Well, for those who take photos. Okay, Clayton, can you lead your friends, Clayton? Let's do greetings.
Stand up. Oh, Miss Prita is rhymes with Miss Prita
Clayton.
they're rhymes because they have the same letter.
Oh
Yes,
yeah,
greeting,
okay, let's do
greeting time.
greetings. Let's do greetings.
Stand up. Stand straight. Greetings. Thank
Thank
you.
you. Thank you,
Miss Prita.
P3A. We eat.
Oh, be useful to others. Thank you for every school. Bless it. Let us thank you.
Bye-bye.